We now take up what is called a free body diagram. This is a graphical trick for solving the net external force on a body to solve Newton's second law. Free body diagrams are in fact quite easy to draw provided you understand the rules about how to draw them. But again, the main reason why we do them is to find the net external force. So you have Newton's second law, and you're wanting to find the acceleration, so first you have to find this side, and you do that with this free body diagram. Once you do the acceleration, if it's constant, you can use kinematic equation. If it's not constant, and you're in the calculus-based course, you might be able to use calculus to then use this to find velocity and position. Or if it turns out that that's very complicated, then we would not attack it with this approach. We'll attack it with another concept like conservation of energy or linear momentum. Let's look at the free body diagram and the steps that one has to do. First, you have to know what body it is that you're looking for the acceleration. We say that your first step is to isolate the body. The reason that you have to isolate the body is there's two things you need to find and know. One is m, so whatever the mass that you're looking for, that's what we mean by the body, and that's what has to be isolated. And also, this word external says that the forces that you're going to include are those outside of the body. If you don't identify the body, how do you know those forces are external versus internal? Now, that simply means that you need to draw the part of the object you're looking for the acceleration by itself. No velocity arrows, no acceleration arrows, nothing, just the object. In the second step, we will inventory the forces. What does this mean? Inventory the forces means we're going to draw force arrows on our isolated body. We're going to start them where the force is applied. This is very important because how a force is applied to an object, a real object, can cause a rotation. And we're going to do it right from the beginning, so when we get to later chapters and deal with rotation, we'll be able to correctly calculate things called torques. So you want to start the force on the body where it's applied, and then you want to draw that arrow in the direction that the push or pull is acting on the body. To find all the forces, we're going to inventory the forces using our little mnemonic want F. That is, these are the only type of forces that can exist on a free body: weight, applied, normal, tension, friction. You may not add any new types of forces. Once you've identified all of those forces, the third step is to draw a coordinate axis. It turns out that the choice of your coordinate axis, well, arbitrary. If you choose in certain directions, you can make the mathematics much simpler. And if you choose the coordinate axis in a different way, it can make the math harder. We'll talk about in the various videos on pulleys, inclined planes, circular motion, so forth, ways to simplify the math by what you would call a wise choice of your coordinate axis. But anyway, you can never say whether the force is in X, Y, or break it into its components if you don't have a coordinate axis. You always must have a coordinate axis in physics. And last but not least, you want to label all critical angles and dimensions. What does this mean? This means that if one of your force arrows is not lying along one of your axes, either X or Y, then you're going to have to use trig to break that vector up. And that means that we need to know what the angles are in order to find sines and cosines. What is this dimensions? Well, at the early part of the course now, we're still treating everything like it's a particle that has no size. But later on, when you deal with something like a bridge or a larger extended object, then because it has size, where you apply the force is important, again, because of rotation, and we'll need to calculate torques. These torques will have to have the distance from a particular point where you're calculating the torque for that axis to the point where the force is applied. So we need these dimensions on the drawing. We need to know, for instance, where the weight is and how long the beam is. So we'll see that later. We won't have any dimensions right now, but I put that in so that every time you draw a free diagram for the rest of your life, this set of 4 steps will account for anyone. Now, the best way to learn any of this stuff is to actually do it. So what I'm going to do is take some problems that have been on old tests, homework, such, and I'm going to just show you how to draw a free body diagram for different little situations. So in the diagram here, we can see a set of blocks and a pulley, and we're asked to actually work this problem. Now, the pulley in this case is what's called a physics pulley and doesn't have mass. We talk about that more in later case. But I'm asked to draw in part 1 the free body diagrams of the block big M and little m. First step is to isolate the object. So there is block M. So this is going to be F, B, D, number M. And over here I draw a small block that represents the free body diagram for little m. That's step 1. Easy. Just draw the blocks. Only the object you're looking for. So you do not draw the table or anything else. You don't draw this velocity area. You just isolate the object that you want to find the free body diagram for. Step 2. On step 2, we are supposed to go and inventory the forces. First, we find the weight. The weight starts here in the middle and points straight down toward the planet Earth. And that will be, I'll call weight 1. Over here, we have weight, starts in the middle, goes straight down. I'll call this weight 2. Subscripts are necessary because they may not have exactly the same weight. Step 3, applied. Applied means is something later in courses, electric fields, magnetic fields. It could be a spring. It could be Johnny. They could say there's a certain force applied to it. Could be air drag. In this case, there is none of that. There's no indication that, for instance, somebody was shoving this block. Third force, normal. That means there has to be a surface of contact. This surface here is the only surface of contact. So the force starts there and it pushes those two surfaces apart. So it goes up like that. Since there's only one of them, I don't have to put a subscript, but it would not be wrong to put one if you want it. T, tension. Are there any ropes? Yes, there's a rope right here. It's attached here and it pulls the block. Now, it turns out that because of this thing called a physics string, we're only consider this to have no mass. We don't consider this to have mass. We don't consider that string there to have mass. So it's as if this block is pulling on that block. By the third law, if little m pulls on big M with a force of a tension T, then block big M must pull on little block M with the same type of force, a tension force. It has to be the same magnitude, T, and it has to point in the opposite direction. Now, this may not seem like the opposite direction, but from the physics point it is. And the reason it doesn't point exactly the opposite like here is because we've talked about these being no mass. And I'll talk about that later in a video. But what you can see is that if this guy pulls this direction, what happens is this block moves this. So you can think of this as like X, and this block moves the same way. We're going to rotate his coordinate frame like this. That's kind of more advanced than what I'm into in this video. What I really want to do in the video is just show you that we need to have T and T. Alright? And the third law, if you make this T1 and T2, they become different variables. You'll need to apply the third law somewhere. F, is there friction? It says there was friction, so as this block slides this way, I know that friction pulls back this way. If you don't know this yet, it's okay. We'll pick that up in a later video. So you isolate the body and then you add vector arrows. And the vector arrows you add are those of 1 to F. After you do that, you've got to draw a coordinate axis for each body. Now you can draw that axis right on the object, or you can draw it to the side. I often like to draw mine on the object, kind of like this. This is X, this is Y, and I am the master. I can choose. It turns out, we'll find out later on, that when you have a problem like this, it's advantageous to rotate this axis by what's called the rule of the gun. I'll let you look ahead. But the bottom line is there has to be axis. Step 4, find the critical angles and dimensions. There are no critical angles and dimensions here. All of these vectors lie in either just the X direction or just the Y. If they came off at some angle like this, then you would need an angle to break them into their X and Y components. In this case, there isn't any of that. So it's simple. You just isolate the body, inventory the forces, put on a coordinate axis, and last but not least, label all the critical angles and dimensions. Best way to do free body diagrams is to practice. And so we created a handout with lots of situations for students to practice on.